Okay, one announcement before the class. There are two assignments are out on the class page. These are about writing RISC-V assembly program. Okay. The first one is very simple, super easy, and second one is taking time. Okay, so you have to plan ahead. Okay, so due is next Wednesday and 2 weeks, more than 2 weeks from today. Okay, third assignment. What you have to do is you have to install. Okay, if you click on this, you have to install a RISC-V simulator called Jupyter. Okay, Jupyter is located. Scroll it down here. Okay, install Jupyter. Download it from here or from here, right? And there is a sample program. This one, simple add.s. This one is simple sample assembly program you can use for second assignment. Okay, and so before you design your own RISC-V CPU, after midterm exam, this Jupyter RISC-V simulator is going to be your CPU. Okay, before you design your RISC-V CPU, real actual hardware. Okay, this one it will be your RISC-V CPU. That means Jupyter is able to execute the program. Okay, RISC-V program you are going to write. Okay, for assignment. For these two assignments, you have to write RISC-V assembly programs, and Jupyter. This Jupyter is able to execute the programs. Okay, and we will talk about these assignments on Wednesday's class because you need to study some more RISC-V instructions to do these two assignments. Okay, so we will talk again about these two assignments on Wednesday's class. All right. So now, okay. Now let's talk about memory access instructions. Second category of instructions every CPU should provide. Okay, including RISC-V memory access instructions. Okay, so before talking about memory access instructions, I'd like you to think. Why do you think CPU should provide memory? So I'd like you to think, why CPU should access memory. Okay, so that is simplified computer structure, right? You have CPU and memory, and location information is delivered through this connection called address bus. Okay, something like 32-bit address bus. Okay, and data is coming in. Okay, data is coming in, or instruction is coming in, and sometimes data is coming out from CPU and stored into main memory. Right? I already answered that question, but I like you to think, why CPU should access main memory, right? The thing is, your program, right? Your program, for example, sorting program you write in C language course, bubble sort, insertion sort, quick sort, sorting program, right? And that is composed of instructions, okay? Instructions, a lot of instructions, and data you want to sort, right? So your program is composed of two big, part, instructions and data you want to, manipulate, sort, right? That is given to you. So given this environment, think about that. Why CPU should access memory? Two reasons. Okay, two reasons. First one, very obvious reason. First one, okay, here, this one. Yongsop, can you please?
Yes. Why should CPU access memory? Initially, everything will put data to main memory. CPU should access main memory to execute your program. So, to purpose, instruction read, CPU reads instructions from memory. Data read and write. CPU reads data from memory and writes data to memory.
Okay, thanks. The first obvious reason why CPU should access main memory is because CPU need to read instructions, right? So many different instructions stored here, like addition instruction, subtraction instruction, and so on. So CPU should read instruction. That is called instruction patch. Okay, instruction patch. CPU patch instruction patch, right? And execute it. That is obvious reason. Okay. And second reason why CPU should access memory is because of this data, right? CPU should bring in many data stored in main memory, right? So CPU bring in this data to do some, processing, some addition, subtraction, some comparison, and so on. So according to, depending on, so some instructions, the instructions we are going to study today, that instruction like LW instruction, load instruction, store instruction, LW. These are examples of memory access instructions. Those are load instructions, load, right? Load, right? And store, okay, opposite operation, store, okay? Those are memory access instructions, okay, memory access. So when CPU execute memory access instructions, okay, for example, load instruction is asking, okay, please read this data and store into some register. Okay, store instruction. So CPU read to instruction patch and execute store instruction. And store instruction says, okay, please store some data, the data in register file to memory. So load, read operation and write operation. So instruction, okay, load instruction, store instruction, CPU execute, that is asking to read those instruction, those data, bring in those data, and store the data back to main memory. So read operation, write operation. Okay. So two reasons why CPU should access main memory. Okay, first one is instruction patch, and second is CPU should read the data, okay, from main memory to register file before addition operation, for example. Okay, after addition operation, for example, then CPU should store back the data to main memory. So that is directed by instructions, memory access instructions. Okay, let's talk in detail about these two. Okay, so first instruction patch, instruction read or instruction patch. Okay, so this one. All right, this one. So I can see only names. I don't know who is who because I cannot see your faces, right? Okay, Jisang, can you please? Hanjisang.
Instruction access. Read. How does CPU read instructions from main memory? Every CPU has a special register that keeps track of current instructions, location, address, and execution. Many CPUs use the same term, program counter. Lec7 also has a 32-bit special register called PC inside the CPU. PC is initialized with a predefined address at reset. x86 fetches the first instruction from this one, and ARM fetches the first instruction 0. Lec7 is implementation fine. PC gets updated as or after each instruction gets executed.
Okay, thanks. For instruction patch, for instruction read, CPU, every CPU, not only RISC-V, but Intel, the smartphone CPU, every CPU has very special register called program counter. Every register, every CPU, not only RISC-V, program counter. This is special register. Okay, that is indicating the location. Okay, which location in memory you need to read the instruction from. Okay, again, CPU, every CPU. Okay, so let's focus on RISC-V. RISC-V has very special register called program counter, which is 32-bit. Okay, and that is initialized when you reset, when you turn on computer. Okay, if you turn on computer, if you press the reset button on computer, that is connected. Actually, reset button is connected to this program counter. So a program counter can be designed with flip-flops, right? Flip-flops, 32 flip-flops, clock, and D and Q. Okay, input and Q output. So program counter register, that is program counter register. So that location PC register. If you have 32 bit. Okay, then this is a plain flip-flop. Okay, it is data input and Q output, plain flip-flop. But for implementing this program counter, you need to use flip-flop with additional input called reset input. That is actually connected. To the reset button computer, right? This button. If you press the button, okay, on computer, that is initializing this program counter. Think about that. When you have that question when you turn on the computer, when you turn on the smartphone, where is it reading the first instruction from? Have you thought about that question? You turn on Intel computer, your desktop computer. You turn on Macintosh, turn on smartphone. So where is it? So where does the CPU inside the smartphone read the very first instruction from? Have you got that question before? The answer is this program counter. When you turn on the computer, this CPU program counter is initialized to some predefined value like this. Intel x86. Intel is starting. Program counter is starting from this, this big number, 7Fs and 0. Intel computer. Okay. And smartphone CPU ARM. ARM is reading very first instruction from location 0. Okay. And RISC-V specification says it is implementation defined. Okay, that means depending on the vendors, Samsung may implement RISC-V CPU. Intel decided to implement RISC-V, design RISC-V CPU. LG, right, decide to design RISC-V CPU. Depending on their implementation, the program counter initial value of program counter varies. Okay, so to make it simple, let's assume that when you turn on the computer, program counter is initialized to 0. For simplicity, okay, okay. So how to implement the initial value? By connecting reset input, right? Reset input, okay, button. Then program counter will be 0. Okay, so like this, clock is coming in. This clock, CLK, and you press the reset button. Like you press the button, then like this, it goes high. Okay, during this time, you press the button and release it here. Okay, then PC program counter will be 0. So from here will be 0. like this value, program counter. This is a waveform, right? Waveform. We will talk in detail about that. Time, right? Time goes by like this. Then if you press the button, then PC is initialized to 0. Okay, so that CPU can read the first instruction located location 0. Okay, location 0. Then read the first instruction, whatever it is. Let's say it is addition instruction. Second, subtraction instruction. The end instruction and so on. So CPU read first instruction and execute it. Okay, program counter. So very super important, right? So program counter is pinpointing the location where the instruction the instruction CPU is going to read from. Okay, it is pinpointing the location. It is address, in other words, right? Address, location, right? Memory location or address. In Korean, 주소, right? 주소, address, location, right? From this location, CPU is patching the instruction from. Okay, very simple. And the thing is, program counter, after reading the first instruction and execute it, then program counter will be automatically incremented. Okay, by CPU. It is automatically incremented. In case of RISC-V, program counter will be incremented by 4, plus 4. Why? Because each instruction is 4 byte in size, right? RISC-V instruction, right? 4 byte. This is 4 byte. Second instruction 4 byte. Third instruction 4 byte, and so on. So location. If I write memory location, the first instruction is located at hexadecimal number 0, hexadecimal location 0. Second instruction, subtraction, is located at 4, location 4. And third instruction plus 4, right? 8, and so on. Then C, hexadecimal number, right? 0xC. C is what? 12, right? And then 1, 0, right? 1, 4, 1, 8, and so on. Okay. So you need to add 4. Okay. So next instruction, next slide. Okay. I cook up that animation. Look at this. So example, right? You assume that you have those instructions stored in memory, and the first instruction is located at location 0. Second instruction 4. 8C, right? C is 12, right? 4 plus 8 plus 4 is 12, right? Then 12 plus 4, 16. 16 is 10, right? In hex, right? And like this, 14, 18, 1C, 20, and so on. The memory location. We say, byte address. We'll talk about that. What do you mean by byte address? And program counter. Assume that program counter is initialized to 0. Okay. So we decided to initialize program counter to 0 when you implement. If you don't like when you implement, you can change, right? You can, okay, I don't like initializing this value to 0. Then you can use set input, for example, resettable flip-flop or settable flip-flop. You can connect reset, okay, the button here instead of connecting here. Then program counter will be initialized to all ones, like all Fs. So it is implementation, dependent. Okay. Anyway, program counter. We assume program counter is initialized to 0. So that information is delivered to memory through address bus. This connection. Okay. Then the instruction at that location which is SW instruction. That is coming in. So CPU, executed. Okay, so CPU just executed first instruction. Then again, program counter is incremented automatically by CPU. Okay, 4 plus 4. Then that information is delivered to memory through address connection, this physical connection. Then the instruction at that location, which is addition instruction, is read and coming inside the CPU, and CPU executed. Then program counter gets updated, okay, to 8, add plus 4, right? And then that information is delivered, okay, to memory. And then instruction at the location is NOP, no operation. It happens to be no operation that is coming in like this, and CPU executed. CPU keeps doing that operation forever. Okay, unless you turn off the computer, CPU keeps doing that operation forever. Okay, so what do you mean by forever? CPU read next instruction. Okay, that is updated to C12, that is delivered, and the instruction at the location LW is coming in, executed, and program counter will be 10. Okay, then the instruction at the location. Okay, so LW, second LW, that is coming in, CPU executed. That will be done forever, unless you turn off the computer. Okay, unless you turn off your smartphone, the CPU inside your smartphone keeps doing that operation forever. Okay, so that is about instruction patch. Any question about this? The first reason why CPU should access memory. Why CPU should access memory? Instruction patch. And for instruction patch, you have a special register called PC. And that is initialized to some value, predefined value, depending on implementation. Okay. For simplicity, let's assume PC is initialized to 0. Then CPU, if you turn on the computer, CPU will read the instruction from that location, right? 0. The first instruction executed, and program counter will be automatically incremented by 4. Why? Because instruction is 4 byte in size. So next instruction is located at 4, location 4. Right? So second instruction is coming in, CPU executed, and PC incremented by 4 to 8. So 8, right? So that instruction is coming in, executed, PC 1 to 12, right? C, in other words, in hex. C. That instruction coming in keeps doing the operation forever. So CPU is more simply to make it simple. CPU execute first instruction, second instruction, third instruction, fourth instruction, and so on. Keeps doing that operation. Right? Okay. Then second reason why CPU should access main memory, data access. Okay, data. Okay, you want to process data, whether big data processing, right? AI data processing. So anyway, CPU should do some data processing. So for that, CPU should bring in data. Okay, then do some operation. Okay, this one, Yusang, can you please?
Data read and write. As mentioned, everything is stored in main memory. You define data to be used in your code, and you sometimes define complex data structures such as arrays and structs. CPU has a limited number of registers inside. There are many data in your program, much more than registers inside CPU can accommodate. In RISC-V, there are 32 general purpose registers inside the CPU. So CPU is able to keep only a small amount of data in registers on the fly. Thus, RISC-V and all other CPUs must provide instructions that transfer data between memory and registers. Such instructions are called memory access instructions. To access data in memory, the data transfer instruction should supply the memory address.
Okay, thanks. The reason why CPU should access main memory, second reason, the data access, right? And when you write program, you are declaring local variable like this, right? You are declaring ABC, 3 local variables, and array of 100 elements, right? So typically you have a lot of data to process. Assume that you have 1 million data, right? 1 million data process. And what should happen is data, okay? 1 million data. So each data should be loaded to some register. First data, second data loaded here. Then you can do some processing like addition operation. But the problem is you have only limited number of limited memory, very small memory inside CPU, okay, called register file, super small memory. So that memory is able to hold only 32, x02, x31. Okay, it is able to hold only 32 data. So what should happen is you are loading some maybe 10 data, okay, 10 data one by one, then do some processing, and to process next chunk of data, you have to make room. Okay, you have a limited number of registers. Okay, so you have to make it vacant, make room. Okay, to make room means okay, the output, the processed output result should be stored back to main memory. Then you are safe to reuse that register because you backed up, right? Backed up that data. To bring in, you can bring in new data inside register file. Okay, so after processing, okay, you have to make room for next data. Make room means you have to write back. Okay, store processed result data back to main memory because main memory is huge. So read operation, okay, read operation and write operation, data read and write. Okay. So for that, RISC-V is providing memory access instructions, memory read instruction, and memory write instruction. Okay. So one example. So we haven't studied LW instruction, but let me explain that instruction. Okay, we will talk LW instruction right after this slide. But I thought it is very important to see a big picture first. That is why I prepared this animation. Okay, so take a look at this animation. It took me one whole day to create that animation. So what is LW instruction? Okay, so before that, we are going to execute these 3 instructions. Okay, these 3 in this animation. So first LW, second LW, then addition. So what is the purpose? We want to add these 2 numbers. That is the purpose of that program. Okay, very small program, tiny program. So we want to add these 2 numbers. Then to add these 2 numbers, you have to place these 2 into register, then do addition. Okay, so first to look at this. First to memory read LW, load instruction. So LW, first instruction LW, X2 and 4, X5. We are assuming X5 contains X5 register. Okay, X5 register contain 1 0. So that means this instruction is saying, okay, read data from this memory location and store into X2 register. What is the memory location? That is computed for 10 X5 plus 4. So that means X5 contains 10. So that means hex 14. So from memory location 14, okay, read the data and place into X2. So that means it's one. Okay, this. Location 14, you have this data stored. And location 18, you have this data stored, right? So first instruction. So X5 is 10 in hex. 10 plus 4, 14. So from this memory location, read the data and place into X2 register. And second instruction, read the data from 18, right? 18, 18 in hex, 10 plus 8. 18 in hex, which is this place. So data will be placed in X3 register. Okay, and third instruction is reading these two, X2, X3. You just stored to these data too, and then output will be stored in X2. So let me show you animation. Okay, very simple program. So program counter is initialized to 0. So that is delivered to memory like this. Okay, instruction patch, right? So first instruction is coming in. Okay, now CPU is about to execute that instruction, LW instruction. To execute that instruction, CPU will do addition operation to compute memory location. Right? CPU, understand, okay, LW instruction, then, okay, I need to create memory location. Okay, how to create memory location? X5 plus 4. ALU, right? This ALU can do that operation. X5 plus 4. So that information is delivered through the same connection. Okay, so 14 is delivered to main memory through the connection, and data at that location is coming in and stored in X2 register. Okay, so CPU just executed the first instruction. CPU executed. Then what should happen next? What should happen? So program counter, right? Program counter should be updated, should be incremented by 4. Yes, Jayan, right. Program counter should be incremented by 4. Okay, so 2, 4, 0 plus 4. So that information is delivered to main memory through the connection. So the instruction at that location, which is LW, second LW, right? Load instruction is coming in like this. Then CPU, okay, CPU interpret. Okay, what CPU look at this instruction, then interpret. Okay, what should I do to execute that program? Okay, this is a memory access instruction. To access main memory, I have to compute memory location based on these two, 8 and X5. So using this ALU, same ALU, X5 is applied to supplies through the first connection, okay, and 8 is encoded in the instruction itself. So 8 is delivered, okay, to second connection. So ALU will do X5 plus 8. So that output happens to be 18. So from, okay, let's go back. Okay, from memory location 18, okay, the data is coming in and stored into X3 register. So second instruction is done. CPU just executed second instruction. Then what should be done next? What should happen next? Second instruction got executed by CPU. Program counter, right? Program counter is incremented by 4 to 8. 4 plus 4 to 8, right? 4 plus 4, 8. So that is applied to main memory. And then instruction at that location, which is addition, is coming inside. Okay. So then CPU interpret. Okay, okay, this is addition instruction. What should I do? Okay, I need to read these two source operand, last two, right? X2 and X3. Two source like this. Okay. Then ALU will do addition operation because addition, right? So addition output will be stored in X2 register. Does it make sense? What do you think? This is the operation CPU computer is doing. More than 70% of the operation computer is doing. If you understand, if you are comfortable with this animation, you are in a very good shape. Any question about this? Could let me know? Could you let me know about? Yes, Yongsub, yes. We will talk about that instruction in detail, LW, but yes, that is correct. X5 plus 4. CPU should compute to execute that instruction. LW, right? Load word, memory read instruction. LW load, right? L load word. That instruction, memory read instruction. You are reading just one data, 32-bit data. To read the data, you need to let memory know the location information, which is specified here. Location, memory location information. How to compute? X5, yes, X5 plus 4. This one, addition. Okay. So, yes, any other question about this operation? So your program, right? So the reason why we want to use computer is basically to process data, right? Data processing, whether it's big data, AI data, whatever it is, right? We need to, process data. This data, to process this data, you have to place the data into register file first. Who is directing? Okay, who is directing that operation? Your program, right? Your program, that program specifically says, okay, read this data, the first data, 11, right, 0011, place that data into X2 register. And your program says, okay, second data, please, place second data into X3 register. Then addition operation. So your program is specifically saying, okay, place this data to here, this data to here, then addition, and so on. Okay. Does it make sense? Any question? Okay, let's move on. Then let's talk about some, one important terminology. This one, Yunsu, can you please?
Word is term for the natural unit of data used by a particular computer design. A word is simply a fixed size group of bits that are handled together. The number of bits in a word is an important characteristic of a computer architecture. The size of a word is reflected in many aspects of a computer's structure and operation. The majority of the registers in the computer are usually word-sized. Modern computers usually have a word size of 32 or 64 bits. The word size of RISC-V is 32 bits. In x86 case, The word size is still 16-bit because of the historical reason, even though your computer is 64-bit CPU-based machine. Alignment restriction. The memory address of a word must be on natural word boundaries. For example, memory address of accessing a word should be 0, etc.
Okay, thanks. Probably you have heard this terminology a lot. If you are, you study computer word. What is word? Okay, so road word, right? Road word. What is word mean? Okay, word means natural unit of data used by particular computer architecture. So what do you mean by that? Simply speaking, very simple concept. We are talking about 32-bit CPU, right? 32-bit CPU. What is the meaning of 32-bit CPU? The data path. Okay, the path data is traveling through. So ALU, for example, ALU is taking two 32-bit data, right? 32-bit, 32-bit. Output is 32-bit. So that is natural unit of data processed by CPU. So 32-bit CPU, word is 32-bit, simple. Super simple, right? Word is 32-bit in 32-bit CPU. So 64-bit CPU, 64-bit CPU, word is 64-bit. Super simple, right? But x86 case, Intel computer, there's an exception. Word size is still 16-bit because of historical reason. I showed the roadmap and I showed the major product Intel produced from 1970 to today, right? In the very first class, Intel started with 4-bit, 8-bit, 16-bit, and 32-bit. Now 64-bit computer, right? And then Intel used 16-bit word, okay? Back in I think 1980s. At the time they used this terminology word. Okay, word is 16-bit. Okay, so to avoid confusion, Intel computer 16-bit, word is 16-bit, and computer you use today now, right, your computer 64-bit based. So 64-bit is quad word. Okay, and 32-bit is double word, right? Double word, right? Quad word. Okay, double, right? Quad, right? By 4, right? So Intel is the exception. Okay, but the other architecture, word is natural unit of data used by computer, right? RISC-V CPU, right? In our case, 32-bit. Okay, so in the previous example, this instruction says load word, LW, load word, one word, okay? Read one word, right? One word means what? 4 byte, 32-bit, 4 byte, 32-bit, right? Load 32-bit, 4 byte data into some register. Okay, this register is also 32-bit. Size matches, right? Same size, 32-bit data placed into same sized register, 32-bit, 4 byte, 4 byte. Size matches, right? 4 byte. Okay, so let's talk about this address. When you access memory, so this one is maybe confusing first time if you study computer. Okay, Intel CPU calculation is on 16-bit unit. No, Intel CPU calculation is done in 16-bit unit, even though register is 6 point. No, 64-bit. Jiun. Probably you are confused because of this explanation, right? What is 16-bit, right? No, Intel computer. The Intel computer you use now is 64-bit based, right? x86. So register file. Their register name is like this: RAX, RPX, RCX, RDX, and so on. And then it has ALU inside, right? ALU 64-bit, right? 64-bit architecture. So data path is based on 64-bit. 64-bit. So this register file, each register is 64-bit in size. So the basic unit of data processing in Intel, 64-bit, because 64-bit computer still. Right? And the previous slide is saying just this terminology word. Okay, Intel, this data size, Intel call this data size to quad word instead of word, even though that is basic unit of data processing. Okay? Because back in 1980s, Intel Intel used word to refer to 16-bit data. Okay, but what if Intel says, okay, now word is 64-bit? Then it is confusing. Word is 64-bit or 16-bit? Confusing. So Intel decided to use, okay, word is still 16. Word is still 16-bit, and 64-bit we are going to call this quad word. Okay, 32-bit we are going to call this double word. Okay, yeah. Okay, still, yes, still, 64-bit architecture, basic unit of data processing, 64-bit. So Intel computer is able to process super big data, right? How big data you can represent with a 64-bit, super big, right? 2 to the power, unsigned number, right? Number 02, 2 to the power of 64 minus 1. It is able to handle these, super big, numbers, right? Yes, thanks for the question. So when you access memory, when CPU access memory, the basic unit of accessing memory, so I would say, minimum unit. The minimum data unit CPU can access. Minimum data unit CPU can access data. So minimum data unit CPU can access is byte. Okay. So you can think of this memory. Memory is organized. Main memory is organized. Logically organized with byte. Okay. Okay. Let me take it back. Main memory is logically divided into byte. Okay. Main memory is logical, not physically. Okay. Logically divided into byte. Okay. And that is byte is a minimum unit of data CPU can access. What do you mean by that? Minimum unit of data CPU can access. So CPU, memory is logically divided into byte. Okay. Byte. The first byte, second byte, third byte, and so on. Right? So that means instruction. Right? Instruction is stored. First instruction is stored here, which is addition instruction. Okay. Second instruction is taking 4 byte in memory, right? Let's say it is subtraction instruction. Okay. And so on. Right? And the data. Okay. And data Same thing goes to data. Okay, the first data, first byte, second byte, and so on. Right. So if you declare some local variable int, okay, a, okay, and that is represented with 32-bit in computer, a local variable a. So then that is taking a 4-byte a. Like this. Okay, and I told you, right, minimum unit of data you can access from memory. Minimum amount of data you can access from memory is byte. Okay, so this byte, first byte, second byte, okay, second byte, third byte, and fourth byte. So you can read, CPU can read, okay, CPU can read this specific byte. Okay, also CPU can read this specific byte. But the question is then, there is a minimum unit. Then question is, can you access, can you read only that specific bit? 8 bit, right? 1 byte. Can you read, this specific bit, 1 bit? Can you read, CPU can read this specific bit, 1 bit only? No, it cannot. CPU cannot read this one specific bit. Then what do you have to do to check out this bit? You have to write program. Your program should read this entire byte, then do some AND operation. Let's say you want to take out second bit, right? Second bit. First bit. Okay, let me take the second bit. Last one. Let me make it simple. You want to read the last bit. Okay. Then what do you have to do? You have to write program. You read 1 byte using LB instruction. Okay. Load byte instruction. This is load byte instruction. L byte. Okay. I want to read just 1 byte. Okay. Not word, right? Last time we talked about LW instruction word. LW is 1 word, right? You want to read 4 byte. But that instruction, I want to read only 1 byte. Then after reading 1 byte, then you have to do AND operation with what? With 0, 0, 0, 0, 0, 0, 0, 1 to take out that information. What I'm trying to say is the minimum unit of data you can access, minimum amount of data CPU can access is byte. CPU is providing, that means CPU is providing byte address. CPU is providing this address line, right? Connection between CPU and memory. That is address, right? If you don't say anything, that is byte address. Byte address. CPU is providing byte address. Okay. Then the data at that location is coming in. Okay. Depending on the instruction you specify, byte or word. If you say word, then 4 byte. 4 byte are coming in. If you execute LB instruction, then 1 specific byte, okay? 1 specific byte is coming in. But you cannot access, 1 specific bit because byte is the minimum unit of accessing, data, accessing memory. Byte, that's the minimum. Because byte is so useful, right? So if you think about C, C language, cha, right? Character, right? A, B, that is represented with 8-bit, 1 byte. If you say what short data type, right? C and D, that is represented with 16 bit or 2 byte, 1 byte. Int, if you use int data type, and that is represented with 4 byte, 32 bit. If you say a long data type, B, that is represented with 64 bit or 8 bit, 8 byte. So depending on data type, computer is using different, different width of data, to represent those the local variables, right? And byte is used very frequently. Byte is used very frequently, and 2 byte, 4 byte, 8 byte data. So that is 1 byte. Byte is minimum unit of accessing main memory. So again, if you don't say anything, CPU is generating byte address. CPU is generating byte. If you don't say anything, that is byte address. Okay, so main memory is organized, okay, logically divided into byte. So first byte is located at 0, second byte 1, 2, and so on, like this. Sometimes people want to use instead of byte address, sometimes people want to use word address. Then look at this. Word is what? In RISC-V case, word is 4 byte in size. Okay. So in byte address, first word is located at 0. Second word is located from location 4. Right? 4, right? 4 byte, right? 4 byte, 4 byte. And third byte is located from location 8. But if you say there's a byte address, but if you say word address, then like this. First word is located at word address 0. Second word is located at word address 1 and 2, 3, and so on. So it is very easy to get that word address, right? Byte address 0, right? Byte address 4, right? And then byte address 8. If you represent that, if you write this hexadecimal location to into binary number, 8 is what? Binary number 1, 3 zeros. 4 is what? 1, 0, 1, 0, 0. 0? Simple, right? 0, 0, 0, 0. So if you remove last 2 bit, if you remove the last 2 bit, that will be word address. 0, 1, 2, and C, right? C is what? Next one, 0xC. C is what? 1, 1, 0, 0. Right? So if you remove last 2 bit, then 3, right? 0, 1, 2, 3. Right? So you can get word address. Word address is word address from byte address. Simply removing last 2 bits. Because last 2 bit is what? Last 2 bit is differentiating, right? Differentiate which byte, which byte within that word you are talking about, right? Last 2 bit, right? 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. So that last 2 bit is saying, okay, that specific byte or that this one. Okay, so same thing goes to here, right? 0, 0, 0, 1, 1, 0, 1, 1. So last 2 bit, okay, last 2 bit is referring to particular byte within that word. within that word, right? So by ignoring last 2 bit, by ignoring these 2 bit, last 2 bit, you get word address. Simple, right? So the important thing, the minimum unit of data, CPU can access is byte. That is why the address CPU is providing is byte address. So if you don't say anything, if you say just address, that means that is byte address. Okay. If you don't say anything, okay, address, then that is byte address. Okay, so let's talk about first instruction. Okay, this one, 조재건.
LW reads a word 32-bit from memory and wrote into a register I-type instructions.
Okay, yeah, that's enough. Thanks. LW instruction, the first memory access instruction, LW I-type instruction. I-type. So this is an example, right? This instruction, you want to read the data from, look at this, data from this memory location, S3 plus 24. Okay, then store that data into T0 register. That is an instruction encoding. Okay, encoding. So I type, right? Immediate RS1, function 3 RD, OP code, right? So the first operand goes to RS1. This is immediate. Okay, offset. We call that offset from S3. How far? Okay, I have a slide, right? I have a slide for that offset. Okay, so S3. So graphically, you can draw like this: LW, T0, 24, S3. So from that location, S3, the offset is base location, location S3 is indicating. Okay, I'm talking about that location, S3. And then 24 is offset from this base. How far? 24 byte away. Okay, 24 byte away. Okay, S3 plus 24. Location is from this base 24 bytes away. Okay, that is the data I'm talking about, right? I want to read the data and store into T0. Okay, so you can think of it as base location. Okay, from the base, how far? 24 bytes away. Okay, so I want to read that data located at that position, the T0 register. Okay, so offset base information, base location is specified in RS1, and offset is specified in immediate and destination RD. Okay, and OP code, function 3, you don't have any control. RISC-V architect decided that number 2 and 5, 2 and 3, and that is LW instruction. Okay, so you can go through that process: binary number and hex number. Okay, so let's move on. So example that instruction. So CPU simplified computer structure, CPU and main memory. So byte address, right? Address or byte address. The first byte is located at 0, 0, second byte 1, and so on. Okay, and assuming you have 2 GB memory installed, then the last byte is located at that position, that location. Why? 2 GB. 2 GB, how many to pinpoint each byte? To pinpoint each byte. in 2 GB memory. First byte, second byte, and the last byte. How many bits you need to pinpoint this location, this location, this location? 2 GB. 2 GB is what? Just ignore byte because the Beijing unit, there is a Beijing unit, 2 gig. 2 gig different byte, right? 2 gig different byte, right? So that means 2 to the power of 31 byte, 2 gig, right? So that means you need 31 bit, at least 31 bit to pinpoint each location. Right? So first location is obviously 0, right? All 31 bits are 0. Then you are talking about this first byte. Sorry, everything is 0 except last one. Sorry, right? Then you are talking about second byte. How about this? All 31 bits. All 31 bits are 1. 31 bits are 1. Then you are talking about the last byte. What is the number in hex? The number. Right? The number 7. 7x. 7 is what? 7. 7 is what? 0, 1, 1, 1. Right? Each is 4 bit, right? Each is 4 bit. So 28 bit. 28 and 3. Right? So then there is 31, 3 bit. Okay. 3, 28. 31 bit. Okay, so so to execute that instruction, CPU will do addition operation. S3 plus 24. Okay, and we assume S3 register contains this value 94. Okay, so 94 is this number in binary, right? 9, 1, 0, 0, 1, 0, 1, 0, 4. Then 24, decimal number 24 is this number in binary. Okay, 16, 8, 16, 8. So 24, right? 16, 1, right? 8. So if you do, math, then you get this number, AC. So CPU will do CPU, ALU, right? ALU will do that operation. ALU will do S3, right? S3 and 24 is coming in. So AC, right? AC information will coming out because that is 94 in hex, decimal number, right? So AC is going to deliver to main memory, okay, through this address connection like this. Okay. AC. So this animation, right? Trying to emphasize the base location. Okay, this instruction says from this base location, which is 94, I want to access data 24 bytes away, 24 bytes away from 24 bytes away from this base location, which is this number. Okay, I want to read this, 4 bytes, 4 bytes, and store into T0 register. Right? LW instruction, load word instruction. I want to read 4 bytes, not just 1 byte. Okay, starting from this AC location AC, I want to read 4 bytes, which is AA, BB, CC, DD. Does it make sense? Any question? Can you use minus sign? Yes, Yongsuk. Yes, you can specify a negative number in offset. For example, minus 24, right? Computer is using two's complement notation, right? LW, T0, you can say minus 24, S0. That means from this base location, S0, base location, I want to access data which is located 24 below minus 24, right? This data, 4 byte. let's say 24 byte. Make it very precise. So the data from this location, 4 byte from the location, minus 24 byte. You can specify negative number. Computer will use 2's complement notation to encode this minus 24. Encode minus 24 to here. Minus 24 will be encoded here using 2's complement notation. Okay. So we'll talk about that. Okay, with example. So this one. So I already explained to you, right? So you can interpret LW instruction like this. So that instruction from this base location, okay, S3 is pinpointing the base location in main memory, and data you want to access is actually located at this offset, okay, offset position. So by using, because LW instruction is using 12 bit immediate offset, right? Offset 12 bit immediate. This is offset, right? And this one is base. According to that encoding, instruction encoding, I-type encoding, 12 bit offset. Then how far you can, what is the range? What is the range of data you can access from this base location range, right? The offset range, 12 bit, right? 12 bit is what? Because we are using 2's complement notation. 2 to the power of minus 11 to this one. I'm talking about the offset, right? 2's complement, plus minus. And then plus 2 to the power of 11 minus 1. That is the memory range. You can access data with that instruction. So that is minus 2048 to this one, plus 2047. Right? So from the base location, from this base location, data can be located this far and this far. Right? So base and offset. So plus and minus. Okay. How about the case of underflow overflow? Rotate like 영섭, overflow, what do you mean by overflow? Oh, what is overflow? Okay, like this. So probably you are talking about this case, main memory, right? Memory, then base location, probably base location S3, and the last, the 20 plus 20, 47, right? 47, which is out of this actual physical memory range. That's what you are talking about, 영섭? Overflow? Then it cannot happen. That is wrong program, right? Wrong program. You want to access main memory, which is you want to access data which is not present in main memory, right? Your main memory size is this big, but you want to access data which is not present in main memory, right? Your program is wrong, right? Is it answering your question? Yes, your program is wrong. You have to be careful. But in computer, we are using, we'll talk about that, almost to the end of this semester, called virtual memory. Okay, but it is too early to talk about that. But in this case, right, you want to access data which is not in physical memory, right? So above that physical memory. So that is, program bug, your program bug. Okay, so that is one. Okay. Okay, so I guess we can, okay, hold on. Let me explain one more, I guess, then. Okay, let me finish, store instruction. It's very simple. Store instruction is doing opposite operation, memory write instruction, memory write. You want to, so in this case, you want to write T2 register, 32-bit data in T2 register into that memory location, right? Like this. Data into T2 register into that memory location. Right? Data T2. Okay, T2 register this data into some memory location, right? Some memory location. Okay, this one is in that instruction case S3 plus 8. Okay, I want to write this data to that memory location. Okay, so encoding is S-type instruction. Okay, so a little bit messy. Look at this. The immediate, right? Immediate is split into two parts, here and here. Look at this format. Immediate here and here. Okay, 7-bit here and 5-bit here. 7-bit, 5-bit. In total 12-bit, still 12-bit, but that is split into two parts. Okay, in instruction encoding. So first operand goes to here, base location RS1, and immediate goes to these two, right? These two part. And this is not destination, right? You are not storing here. This is not destination. T2 is not destination, right? T2 is encoded in RS2. You are storing data in T2 register into that memory location. Data here, location. This is not destination register, right? You are storing to this memory location. So instruction encoding is simple, right? You can do this. Okay, time is up. I guess that's it for today. Any question before letting you go? Next time we'll talk about LB instruction, load byte instruction, load half word instruction, load LP, LH, and there's one thing you have to be very careful with LB and LH. When you load byte, half word, size mismatch, right? You are reading 1 byte and store into 32-bit register, size mismatch. What do you have to do? Size, right? 1 byte, reading 1 byte and store into 4-byte register. What do you have to do, right? Some issue, we have some issues, right? So we will talk about that next time. 베이스 어드레스는 어떻게 설계하시는 건가요? 정원, you are writing program, right? You specify the base location. Because you are the boss, right? You are writing program. You are the programmer, right? No one is specifying the base location. You are specifying, for example, in the assignment, for example, this example program. For example, like this. This simple assignment. Okay. So here, you have 8 data to process. 1, 2, 3, 4, 5, 6, 7, 8 located at this location, OP1. First 4 data are located at this label, OP1, this position. And second 4 data, 5, 6, 7, 8 are located from this OP2, this label. So you can think of it as base location, OP1. If I draw, it looks like this. Memory, right? your program, your instructions, right? And data, OP1. OP1 is located from here. So here, word, in this case, word, right? Word, 4 byte. 1, 2, 3, 4. From that memory location, label, right? Label is memory location. Okay. Function name, right? Also main, right? Function name is also indicating memory location. Think about that. Function name. The symbol is memory location actually. The first instruction, okay, main says the location of first instruction. Main is what? Location of first instruction of that function, right? Main program, right? Main program, right? Main program is composed of many different instructions, right? Addition, subtraction, and label main. Main is pinpointing the location, very first location. The location where very first instruction is located inside the main function, right? Right? Your function is composed of what? 여러분 함수가 뭘로 돼 있어요? 그치? 함수가 이제 인스트럭션으로 구성돼 있을 거 아니야? 컴파일하면 메인 함수, 뭐 fu 함수, 인스트럭션으로 구성돼 있을 텐데 함수의 이름은 처음 그 함수에 있는 첫 번째 인스트럭션을 가리키고 있지. 그 함수에 있는 첫 번째 인스트럭션, very first instruction in that function. That is function name, right? Whatever. Okay, so the answering your question. 영섭's question, 정훈's question. OP1, right? This label you can think of it as base, and OP2, 5, 6, 7, 8. Okay, OP2. You can think of it as another base, right? And first data is located at offset 0. Right? And second data is located at offset 4, third data offset 8, and fourth data offset C. C is in 12, right? X. And operation, second operand, right? You can think of it as a base. You are writing program, right? Base. And then you store this base location to some register, for example, S0 register, this one to S1 register. Shown, right? And second operand, right? First data is located at offset 0, second data offset 4, 8, and C, like this. So you are writing program, you have to initialize base register to some location, right? You have to specify. But if you write C program, compiler, if you write high level program, C, Java, and so on, right? Then compiler will set base address. But if you write assembly program like this, okay? So here, we haven't discussed LA instruction, but LA instruction is setting base location. Right? T0 is base, T1 is base for the first, 4 byte. Okay, T0 is base address for 1, 2, 3, 4, these 4 data. And T1 is base location for second chunk of data. 정원, is it answering your question? Okay. Writing assembly program, you are the boss. You have to do everything yourself. Okay. Okay, any other questions? Okay, I guess then that's it for today. See you next time. Bye. Okay, thanks. Bye.